Hello and welcome back to Gen Chem with Dr. J. I'm Dr. Janita Pritchett, and on this channel we cover all things Gen Chem related. On this video, we'll be covering Hess's Law, and I'll go through steps on how you apply it in actual problems. Let's get started. So if you recall in a previous video where I first introduced enthalpy, we talked about how enthalpy is an extensive property. So extensive properties are those things that are dependent on how much of that material or how much of that substance are present. And so knowing that enthalpy is an extensive property, we can use that information along with the relative mole amounts and the direction in which the equation is flowing to help us to determine what the enthalpy would be for unknown reactions or ones that we haven't studied thus far. And so, for instance, if we know that we have an enthalpy for a reaction of negative 393.5 kilojoules for the synthesis reaction of carbon dioxide, well, if we were to double the amount of each of the reactants and therefore double the amount of product that we get, well, that means that the enthalpy itself would also have to be doubled as well. And so for accounting purposes, we would multiply that number, that enthalpy value, by 2 to adjust it accordingly. Similarly, if we were to reverse the reaction, well, reversing the reaction means that we're actually going to change the sign of the enthalpy value as well. Remember that a negative enthalpy value means that we consider the reaction to be exothermic, which means it's releasing heat. But if we reverse the reaction where we now have our product become our reactant, in this case, CO2 becomes the reactant, well, that means that that reaction would now become an endothermic property or endothermic reaction, which means that heat is going to be absorbed. And so since we reverse the reaction, we would actually change the sign at which we designated for the enthalpy value. So we can explore these relationships involving enthalpy through this idea of Hess's law. And so Hess's law is really looking at the change in enthalpy for a stepwise process in which it equals the sum of the enthalpy changes of all the steps. And so oftentimes we'll have enthalpy values for specific equations that exist. However, we'll be asked to explore and determine the enthalpy for some unknown equation. Well, typically that unknown equation is the result or can be viewed as the summation of these smaller or different types of equations. And so we can monitor how we have to adjust those particular equations and track those adjustments by adjusting the enthalpy value and overall be able to sum up and get the new enthalpy value for this reaction that we're studying. And so again, if a reaction can be expressed in a number of steps, then the enthalpy for the overall reaction is the sum of the heats of the reaction for each step involved. So let's try an example. So here it says we are given some information about two equations. So we have copper plus chlorine is yielding copper 2 chloride, and it has an enthalpy value of negative 206 kilojoules. Then we also have copper plus chlorine produces copper 1 chloride, and that has an enthalpy value or heat of reaction value of negative 36 kilojoules. We now want to calculate the enthalpy for this new equation, this copper plus copper 2 chloride that produces copper 1 chloride. Now, so what we're going to be really looking at here is seeing, do we indeed have the summation of these known equations? Can we process this and think of this, how this would equate to this overall series of that are needed to create this new equation? So our goal is to manipulate these unknown equations, our goal is to manipulate these known equations so that they would end up equaling our desired equation. So this is our desired equation. So what we're going to do is first focus on what parts of each of the equations appear in our desired equation. And so if we look at the very first equation, we can see that copper is present, and it's also present in our desired. We also notice that copper 2 chloride is present in both of them. After you've identified what's present, you then want to ask yourself, well, is this the only place that I can get this thing that I desire, right? So in the instance of copper, we see that copper is found in both the first and the second equation. However, the copper 2 chloride is only found in this first equation. So what that tells me is I need to focus on manipulating that first equation so that I can get the copper 2 chloride to match the position and the amount that's in my desired equation. I'm going to come back and deal with copper at a later time because since it's found in both equations, there's a likelihood that it'll work itself out at a later time. So again, focus on the copper 2 chloride. And what you should notice is that in my given equation, it's showing up as a product. However, in my desired, it's a reactant. So immediately you should be signaled that, okay, I need to reverse this equation. I need to make my copper 2 chloride become a reactant. And it's always beneficial if you keep the arrows aligned, and make my copper and my chlorine become products. Well, since we flipped the equation, we reversed it, that means that the enthalpy value for this was negative 36. Well, now it would become negative to that as well, which would make this overall a positive, an endothermic process. I can also see that the amount-wise, I'm good. I only need 1 mole of copper 2 chloride, and I have 1, so that works out. Now we'll focus on the second equation. And again, we're noting what appears in the second equation that also appears in the desired. And so again, I see my copper is present. And again, I'm just using different lines so I can distinguish between the two. And then I also see the copper 1 chloride is present. Again, because this is the only place I can get that copper 1 chloride, I'm going to focus to ensure that it matches what I need, okay? And so it's a product in my desired, it's a product in the given. So that means I don't need to reverse the equation. I can keep it as is and just start with my 2Cl solid and keep everybody else in position. Again, it really helps if you try to keep the arrow aligned as you're doing this. And I also just noticed I put the wrong numbers here for the first enthalpy. The first enthalpy, I'm sorry, should have been negative 206. And I am now making that a negative to that. And here on the bottom, we're going to keep it at negative 36 because we did not reverse the reaction. So now we also check to see the amount. Well, I have 2, I need 2, so that should be good to go. And so at this point, once you've put everybody into the proper position, we then are going to be looking for how can we go about actually summarizing, putting these together and getting this desired equation out. And so we're literally going to be adding these two reactions together. Now, things that appear on both sides of the equation, you're going to cancel out. So if you look, you can see that some copper can cancel out. I have copper 1 here. I have 2 on my reactant side, so that means I can get rid of 1. And then I also see the chlorine. I can get rid of that on both sides. And so when we see that, we can then summarize and put these together. What we end up with is 1 copper plus the copper 2 chloride produces my 2 copper 1 chloride. And you can see here when we look at this that indeed it does check out, that we do have the proper equation that we desire. And now we can go about simply adding these things. So if we had the negative 206 that we then made negative, that would become positive, right? So positive 206 minus 36 would give us positive 170 kilojoules. And so if this is the case, we would make a declaration that this is now an endothermic reaction. Okay. Again, make sure that you have the proper enthalpy values listed. Don't be like me, and adjust the numbers accordingly. Okay, we're going to go on to a slightly more difficult one, but it'll just give you some other things to be on the lookout for when you are doing these problems. Okay. All right, so once again, we have this given information. We have these 3 reactions that we know with their respective heat of reaction values or enthalpy values, and our desired equation is found here. Our goal is to manipulate these equations, these given equations, so that they match up and add up to the desired equation. So focus on the first equation first. What appears in the first equation that also appears in the desired equation? Well, I see NO2, and I also see NO. And we ask ourselves, we scan the other ones, is this the only place where I can get either of these things? And what I see is that the only place that we can get NO2 is from this reaction. The nitrogen monoxide, actually, it's in the third reaction as well. And so I'm not going to focus on trying to get that to match up just yet because it may work itself out later. So my objective is to get my nitrogen dioxide to match. Immediately, what I see is that it's on the product side and I need it to be a reactant. So our first objective is to flip the equations. So again, flip it, and we're going to put 2NO2 as a reactant, and then 2NO and O2 here. Well, if we flip the equation, we had negative 116, but now since we flipped it, we need to make that opposite to that sign. We also want to pay attention to the amount that's present. I need 3 moles of NO2. I have only 2. And so I need to multiply by a factor to get rid of the 2 and replace it with a 3. So what I'm going to need to multiply by is 3 over 2, because that allows my 2's to cancel out. But I don't just multiply there. I also have to multiply here, here, and here. Or you can multiply by 1.5. Okay? We can now move on to the next one because that's all the adjustments that we can do so far. If we look at the second equation, what we see is we have some water in our desired, and we have nitric acid. And it looks like this is the only place that I can get either of these two things. And so I need to make sure whatever adjustments I do gets those to the proper position and the proper amount, because I won't have an opportunity to change it again later. And so we look and see that they are indeed on the proper side. So I don't need to reverse the reaction. So we'll first write it as is. And I'm omitting the physical states simply because I need to be able to balance this out and have some space, but you would want to pay attention to those physical states as well. Okay. And so since I did not reverse it, I would keep it at negative 256, no adjustment to the signage. But what we do notice is the amount is not correct. I have 2 and 4 in the given, and I only need 1 or 2 respectively. So I need to divide both of these numbers by 2. So if we divide that by 2, again, remember you have to divide every single coefficient by 2, as well as divide the enthalpy value by 2. And then last but not least, we look at the third equation and we see that we have the NO that's present. And that looks like that's all we have. Now, what you may be thinking is, okay, well, I have some NO and I need it to be on the product side, so I can leave it as is. I can write it as is. However, if we do that, remember, we also already have NO locked in place in this first reaction, and we have 3 of them. And so, in fact, we don't want to leave it in that position. We don't want to, we need to flip this equation in order for us to cancel out some of the nitrogen monoxide to get the desired amount that we need. Because if they remain on the same side of the arrow, we'll be adding those numbers together when we really need to be reducing the amount that's present. We currently have 3 of them present. So we will need to flip our equation. So we'll put 2NO on the reactant side, and then N2 and O2 on the product side. And so since we flipped it, we were at positive 183, but we now have flipped it, so you make that negative. And we check our amounts. Well, we have 2NO, I have 3, so that actually looks like it'll be good. It'll be able to cancel myself out. So at this point, we should be ready to try to add our equations together to see, did we create our desired equation? And so we look for what can cancel out. Things that are on opposite sides of the equation are able to cancel out. So I have 2 over 2 or 1 nitrogen. I also have 1 nitrogen, so that can be canceled. I have 5 halves oxygen. And look, if you look, I actually have 3/2, and this is the same as 2/2, which 2 plus 3 gives us 5 halves. I can cancel those oxygens out as well. And then what seems to be remaining is with my nitrogen monoxide, well, I have 2 on the reactant, I have 3 on the product, so that would give me 1 left over. And so now when we rewrite our equation, we have 3NO2 plus 2H2O produces 1 NO and 2 HNO3. And so since that checks out, that tells me that I can go ahead and do my calculations. So remember, with the calculations, you want to adjust for all the numbers that you've placed in there and the changes you've made for those coefficients. So we have -116, but that became positive. So that becomes 116 times 3 divided by 2, 174. Then we're going to be adding in the -256 divided by 2. And so we will then do my plus sign, parentheses, my 256 divided by 2, and plus, now we have -183 negative. And what we end up with overall is -137 kilojoules. And so when we're defining this equation, we would state that this is considered to be an exothermic reaction because we have this negative value created. I hope this video helped you understand how to do Hess's Law problems. Make sure you guys like, comment, and subscribe, and let me know what additional content you would like to see. Be back for more videos. We'll be covering the rest of our Chapter 6 material and future ones. Have a great day. Talk to you later. Bye-bye.